Okay, a very good morning. Welcome to this lecture. We were talking about three-phase induction motor. We have seen certain relationship of induction motor, synchronous speed, slip. We have also seen the rotor frequency at standstill and when it rotates. So the frequency at standstill is supply frequency. Standstill means rotor is not revolving, it is stationary. When rotor rotates, at that time the frequency becomes slip times supply frequency. Then we talked about rotor EMF. Rotor EMF that will consist of slip times supply frequency, or it will have rotor frequency. So that we have seen, and we come across the expression for rotor current, which is given by this one. What we have noticed here, that the per phase power input to rotor, that will be equal to I2 square R2 by S. I2, the subscript 2 is indicating we are talking about rotor circuit. If subscript 1 is there, then we are talking about stator circuit or stator side. So we have noticed that the input to rotor, that is equal to I2 square R2 by S. Here reactance, the rotor reactance that do not consume power. So we have seen expression for air gap power in different form we have seen. So that could be basically expressed in terms of rotor ohmic loss, and in addition to rotor ohmic loss, it is going to include mechanical power developed in rotor. So these are the expressions what we have seen. We have also seen the electromagnetic torque, that is given by Pm upon omega r, or in case of air gap power is given, so it will be Pg upon omega s. We have also talked about the soft power. So soft power, that will soft torque. So soft torque, that will be given by soft power divided by rotor speed, and the soft power or output power is the power which is available at the soft. So at the soft, what you need to do, the power which is available, that will be mechanical power, subtract the losses, which is mechanical losses. You need to subtract mechanical losses. Mechanical losses means we are talking about here friction and windage losses. So that need to be subtracted from the mechanical power in order to get the soft power. And once soft power is with you, you can calculate the soft torque. Then we talked about losses, under which fixed and variable losses were discussed. So that we have seen. So how we can calculate the variable losses? So variable losses, it can be calculated using your block rotor test. You need to remember, if the motor is your wound rotor induction motor or slip ring induction motor, at that time do not forget to include brush contact loss. So always include the brush contact loss whenever the motor is wound rotor induction motor or slip ring induction motor. The obvious reason is that this particular motor consists of brushes, so you must calculate that, consider that losses. The stray load loss, regarding that, it can be considered by just accounting 0.5% less efficiency in overall efficiency. So that is accounted, and that way it is usually not calculated. Then we talked about the power flow diagram of three-phase induction motor. It means the stages of power. You have given input power, so what would happen on stator side, and when the power is transferred to rotor side, so what will be the power and losses there. So that was discussed in previous lecture. Then we talked about efficiency, that is given by this expression, output upon input, or input, you know that how we can calculate, we can put the value of input in terms of losses and output. So that can be considered. In this case, remember the output will be your soft power. Output power, what you have to consider, that will be your soft power. If you are going to consider the mechanical power, so it is going to give you inaccurate result, because that is actually not the output power. So here output power will be your soft power, that you can keep it in your mind. So in this lecture we are going to talk about induction motor phasor diagram. Okay, so the phasor diagram, that will consist of both the side. One will be your stator side, another one will be your rotor side. So these many things we are going to locate on stator side. So abbreviation is already shown here. On rotor side it would be like that. It is shown on rotor side quantities basically. So that we have to put up in a phasor diagram. So this is a phasor diagram is shown here. On rotor side there will be rotor MMF, which will be given by F2. The 2 subscript is denoting here that we are talking about rotor. So rotor will be having MMF, and this MMF will be lag behind air gap flux by a space angle of 90 plus theta 2. So here, if suppose you have considered the phi as a reference, so you would be in position to draw the F2. F2 can be drawn at 90 plus theta 2. The 2 is indicating here the rotor side, the subscript 2. Again and again I am repeating in order to keep it in your mind that we are talking about rotor side. So the F2, that is the MMF, rotor MMF. So it would be lagging from phi by 90 plus theta 2. So this can be drawn. I2, that will be in the phase with F2. Then F1 dash, that would be opposite to your F2. So F1 dash is nothing but it is your rotor MMF, which will be given by I2 dash N1 dash. Here N1 dash, what it is indicating? It is indicating that N1 into your KW1, winding factor is also there. Okay, in N1 dash. N2 dash, what exactly it is meaning? It is giving you N2 multiplied by the winding factor of rotor side winding, KW2. Okay, so that is N2 dash. So here, once you have the F2, the F1 dash, it will be drawn opposite to F2, that is going to give you F1 dash. Here the I2 dash, that will be in phase or opposite to I2, which will be basically the load component of stator current. Here I2 dash is the load component of stator current. So it will be drawn opposite to this I2. Then you will be having E1 and E2. Basically it will be lag by 90 degree from your phi. So it will be drawn 90 degree from this phi. So the E1 and E2 is shown here. E1, that is showing the EMF for stator side, and E2, it is the EMF of rotor. So E1, E2, that will be drawn at 90 degree. Now you are interested to determine I1. So how I1 would be obtained? The I1, that will be our F1 first you need to find out. So F1, that will be basically the phasor sum of F1 dash and FR. So here what is the FR? FR is your resultant air gap MMF. The phasor sum of FR and F1 dash, that is going to give you F1. What is the F1? F1 is your stator MMF. So stator MMF, it consists of basically two components. One is your F1 dash. F1 dash is here your rotor MMF, and FR is your resultant air gap MMF. Here the resultant air gap MMF, that will be in phase with phi when hysteresis is neglected. So in this case what we have considered the hysteresis has no role, so it is neglected basically. That's why the FR is drawn in line with the FR. So FR and the F1 dash, that is going to give you I1, and your F1. I1 that will be obtained by phasor sum of I2 dash and IM. I1 that will be the phasor sum of I2 dash and IM. What is IM here? IM is your magnetizing current. So this is your phasor diagram. Now what you have to do, induction motor, it has to start. Basically it has stator and rotor, not you need to start. This is the phasor diagram. We will now draw actual phasor diagram for induction motor by omitting this MMF. Here what we have shown here MMF, F2 is shown, F1 is shown. So for better understanding, for a better clarity of induction motor phasor diagram, those are dropped. Now we are going to, with this concept, basic phasor diagram, we are going to understand the phasor diagram during standstill condition, means when rotor is not revolving and when your rotor is revolving. So two conditions we are going to talk about with respect to that previous phasor diagram. In previous phasor diagram, what we have seen, we have seen your I2, how we have obtained I2. So your I2 that will be lagging by 90 plus theta 2. So that is known to us. Your E1, E2 that will be lagged by 90 degree, that is known to us. Okay, and the basic component, the stator current, how it can be obtained, that is known to us. So this is the phasor diagram which is shown for standstill condition. Remember, whenever we are talking about standstill condition, at that time the value of slip will be 1. Okay, the slip is not going to play major role, you could take in that way. So at that time, what would be the value of EMF induced in the rotor? That will be given by I2 R2 plus I2 into J X2. Here S will not come. If somebody wants to write S, then its value is the 1. So this will be your E2. So already we have seen that if suppose your phi is your reference phasor, so your I2 that will be drawn at 90 plus theta 2. So I2 can be drawn. Then what you could draw, you can draw basically the I2 R2 drop. This drop can be drawn, which will be drawn basically in phase with I2 R2, and then this JX2 I2 that will be added to this I2 R2 drop. So here this, when you are adding J I2 X2, you are going to get basically E2. So this E2 will be the 90 degree lagging from phi. Now you could draw E1 that will be also in phase with E2, and the I2 dash that can be obtained by reversing this I2 of same length. You have to draw the same length of I2 in the opposite direction. So in opposite direction, just draw one line of the length of I2, which will be called as I2 dash. Here your I2 dash that will be consist of basically this one. I2 dash, basically I1 that will be obtained by taking phasor sum of I2 dash and I0. How I0 can be obtained? The I0 will be the sum of I0 is nothing but here it is the no load stator current. I0 is no load stator current that will consist of your IC and IM. So the phasor sum of IC and IM, that is going to give you I0. This IC that will be in the phase with V1 dash or minus E1. And how the V1 dash is obtained or minus E1? You are having E1, so E1 that will be extended in opposite direction. So what you have to do after drawing this after getting E2, E1 can be drawn in phase, and the E1 dash can be obtained by reversing this E1. So you are having E1. So in phase with this E1, IC is drawn. The sum of magnetizing current and the core loss component current IC, that is going to give you no load current. You could recall transformer, what we did. Basically the equivalent, circuit phasor diagram, almost that would be in that line only, as well as equivalent circuit, which we are going to talk about. So this is going to give you basically I naught, and once you are having I naught, I2 dash is already with you, its summation is going to give you I1. Okay, now you are having I1, you are having V1 dash or minus E1. So what you could do in order to obtain V1, you can add the drop of stator side. What will be the drop on stator side? There is resistance, stator will be having resistance, stator will be having reactance. So I1 R1 drop will be there, it will be added to V1 dash or minus E1. So this will be added in the direction of basically in phase with I1. So whatever is the line you could see here, I1, you need to draw in parallel to this I1, this drop will be added. And once you have drawn I1 R1 drop, from here you have to take a 90 degree, which is going to, you have to draw a line of this length, you could say, which will be greater than I1 R1. So this is going to give you J I1 X1 drop. Then take a phasor sum, it will give you V1. Now you are having V1, you are having I1. So the angle between V1 and I1, that will be called as power factor angle of stator, which is theta 1. What you could notice here, if you will pay attention, so what you will find out that this theta 1 or cos theta 1, it will be very less. Why? Because the angle is high. You could see what would be the angle here. You could imagine what would be the angle, and you know that when cos 90, how much it is? It reaches to 0. Cos 0 is 1. So when you are having a higher angle, the power factor is poor. So during starting condition, during standstill condition, the power factor would be very poor. This is one of the feature of induction motor. So during starting or at standstill condition, whenever you draw the phasor diagram, you must keep it in mind that the angle should be a wider. Okay, so this is basically the phasor diagram for under standstill condition. Now let us move on. When rotor starts revolving, when motor starts revolving, so what would happen? Now the slip will come into the picture. Now the slip is going to play the role. The EMF equation, the EMF, it will be consist of S, because the rotor is having frequency S time 9 frequency. Okay, it is not shown here, you could see here. So basically I'll show you this later on. First we will discuss this one. So what you could see here, that you are having phi. Okay, I2 will be drawn in the same manner. Once I2 is drawn at angle of 90 plus theta degree, theta 2, at lagging angle I2 is drawn, then you can draw I2 R2. Just add the drop I2 as X2 multiplied by S. See here your rotor voltage, that will be given by this one SE2. The slip is going to come into the picture, S will be there. So your EMF which you have drawn in previous case, that was just plain E2. Here it will be S time E2. Remember this. The drop I2X2, that will be here S time I2X2. It will be S time I2 x2. So here you could see what we have shown here, z s time I2 x2. Here just I forgot to add s, just include s here, okay, in this expression. So what would be, this is going to give you basically s E2. Now you are having s E2, you are in position to draw E1. E1 can be drawn. Once E1 is obtained, you can extend on reverse direction, so that is going to give you V1 dash R, which is equal to minus E1. You could obtain I0 in the same way, like the IC, it will be in the phase of E1, a minus E1 or V1 dash, and you will be having IM, its sum, phasor sum is going to give you I0. Once you are having I0, I1 can be obtained by taking phasor sum of I2 dash and I0. Basically here in I0, one thing you need to keep it in mind, that now your rotor is revolving. When rotor is revolving, so what would happen? There will be friction and windage losses will be there. So that is also added into this one. Okay, here in case of IC, it will become IFC. So that you need to keep it in mind when you are talking about induction motor operation or phasor diagram when it is revolving. So at this time we have replaced the IC with IFC. So IFC is nothing but here friction and windage loss, including the core loss component. So that is IFC. So I0 will be with you. Now I0 is with you. I2 dash, that can be obtained by extending in this opposite direction. So it is going to give you I1. Once I1 is with you, what you could do? You can, now you are in position to draw I1 R1 drop. So at that you need to draw a line parallel to this I1. So I1 R1 is obtained. Then from here just take the 90 degree, that is going to give you J I1 X1, and the resultant is going to give you V1. Hope the things are clear to you. Let me show you. Take a reference phi. Phi is there. After that, what you need to do? Draw your I2 at an angle of 90 plus theta 2. Then you can draw the drop I2 R2 and drop JI2 X2. It is going to give you E2. E2 is obtained, then you can draw E1. After E1, actually either you can go with this E1 dash, because you are not going to get this I0. So that is drawn here. IM can be drawn. So IM is drawn here. Then IC is drawn. In this case it will be IFC, and this is going to give you I0. Okay, you are having I0, and what we have done, we have now drawn I2 dash. Just reverse it, I2. Then this cannot be obtained unless and until you are having this I0. Okay, so for obtaining this I0, what you need to do, before obtaining it, you need to first draw this one, E1 dash. Okay, first that should be drawn, and after that you are going to get this I0. Okay, and once I0 is with you, you are going to get the I1. So this line should be drawn before drawing this one. Okay, so you are having minus E1, now you are having I1, so I1 R1 can be added. Then from here this 90 degree J I1 X1, and this is going to give you V1. It's quite simple, you can draw it easily. The thing is that in both the cases, what was the difference? It was the rotor EMF. It was the rotor reactance. So here both phasor diagram is with you. When motor is stand still, slip is 1. When motor is in running condition, rotor is revolving, at that time the slip is going to come. So what you need to do, you could observe one more thing here, like in previous case what we have seen. Just see the angle between this one, V1 and I1, and here observe the angle between V1 and I1. In first case, the angle is higher, and in another case, the angle is lower. So during operating condition, power factor is better compared to when it is at standstill. So whenever you are going to draw phasor diagram in examination, keep this thing in mind. Are you drawing for standstill condition? Then whenever you draw this I2, take theta 2 as a larger angle. If you are drawing for revolving condition, running condition, so this theta 2 should be smaller. So when theta 2 is smaller, so automatically you are going to get a smaller power factor angle here. This is the difference which you need to keep it in your mind. Almost procedure is the same. What is happening, the S is coming into the picture on rotor side, that you have to keep it in mind. So power factor plays significant role in operation of induction motor. So that you must keep it in your mind. Now let us talk about equivalent circuit. I think the things are clear to you. If there is any doubt, you can ask anytime. Whatever we have seen equivalent circuit in case of transformer, you can follow exact same method. In this case, in case of transformer, there was primary winding, secondary winding, or HV and LV was there. In this case, we are having stator, we are having rotor. So stator will be having your resistance, it will be having reactance. The stator is made of the core, so it will be having the losses. So that losses has to be supplied. In the same way, the rotor will be there. So in this case, what we are going to do, in order to obtain complete equivalent circuit, first we are going to determine individual equivalent circuit for stator and equivalent circuit for rotor. Then we are going to combine it. We are going to club it. So we know, in order to obtain equivalent circuit, we need the expression of voltage for stator side. So that can be easily obtained, because we know that whenever you are going to connect a supply to the stator of induction motor, so there will be a rotating air gap flux, phi will be there, and this flux is going to generate a EMF, which is known as basically counter EMF in all windings, in three-phase winding. And the stator terminal voltage V1, it has to basically overcome the counter EMF minus E1 and the drop across leakage impedance, that is going to include leakage resistance and leakage reactance, sum of that. So leakage, it has to, whatever V1 would be there, it must counter that EMF and the drop, leakage impedance drop. So we are having this expression. So once you are having the expression, you are in position to basically draw this part. So V1, that will be your supply voltage. There is in order to obtain V1 dash, so what you need to do, you need to add this drop. So R1 is there, R1 is drawn, then X1 is drawn. How much current is going to flow in this? That will be your I1. When it is going to add with the V1 dash, you are going to get this equivalent circuit. Here the frequency, that will be your line frequency. We are talking about stator. So the frequency, it will be your line frequency. Okay, so what part we have drawn from this circuit, this equivalent mathematical expression, the outer part has been drawn. Now we know that the stator current, it has to supply to the load, as well as this current has to supply for flux as well as the losses. Exciting current should be there, there will be the load current. So basically the stator current, it will be consist of two components. One will be your load component, I2 dash. So here, till here we have shown I1. After that we have shown here is the load component, which load component of the current, which will be supplied to the load, and the remaining current, which is called as exciting current, this exciting current is going to supply the core loss, it is going to supply the core losses, and it is also going to supply for the magnetizing current or magnetizing component. So basically this exciting current, that will be divided into two parts. One will be the core loss current. So core loss current we are showing here. There are losses in core which will be represented by the resistance, and there will be the magnetizing component. So magnetizing reactance is shown there. So this is the IM. IE, that will be splitted into two parts. Earlier there was I1 stator current. It consists of load component as well as exciting current. So it is divided into two parts. Then this I1 is going to supply the loss component, core loss component, and it is also going to supply for magnetization. So magnetizing current would be there. It is splitted into two again. So IC and IM will be there. So this is basically would be your stator equivalent circuit. So the shunt branch, this branch is called as the shunt branch. Okay. Again, an important question from practical examination point of view. Shunt branch, what it consists of? So what exactly it is representing? It is representing here core loss component and magnetizing component. So two components are there. So this core loss component, basically that will be in phase with V1 dash. Already we have seen, we have drawn here in phasor diagram, the core loss component was shown here, IC, that will be in phase with here. So you can draw it here as well. Okay, so in phase with that. And your magnetizing component, that will be lagging the V1 dash by 90 degrees. So we were drawing it here. This is your V1 dash. So we have drawn it here. You could see 90 degrees. The core loss, we know that it can be obtained by subtracting friction and windage losses and small I square R losses, which will be at no load from no load losses. So you have, when you subtract these two, you are going to get the core losses. Then let us talk about rotor circuit. This already we have seen. For rotor circuit, what we have this expression. Okay, we are having this expression. We can rewrite the rotor current expression into this form. Correct? It means we are having two different expressions. So if you are drawing the rotor equivalent circuit, we will be having two different rotor equivalent circuits, which is shown here. When you are considering this expression, this will be your rotor equivalent circuit. When you are considering this expression, this will be your rotor equivalent circuit. So there is slight difference. What difference you are considering? What you could see here, in this case, the rotor EMF, it is at rotor frequency, at slip frequency. In this case, what you could see, the rotor EMF is at supply frequency, line frequency, on plane E2 is there. Here you could see that the rotor resistance is constant, it does not depend, it is not varying with the slip. But in this case, your rotor resistance, that is varying with slip. That's why the variable sign is shown here. You know that what exactly it is indicating, that the value of resistance can be changed. So it is going to vary as slip is going to vary. Here the rotor resistance, it will be not affected by slip, but the rotor leakage reactance, that depends on the slip. So the slip is going to decide the value of leakage reactance. In this case, the leakage reactance is constant. So basically, if you are using this expression, so the rotor equivalent circuit, that will be drawn at a frequency of rotor frequency, S time F, supply frequency. and this is drawn at a supply frequency only. So this is the major difference. Whatever rotor circuit you would like to use, you can use, but it has certain advantage. So basically we are going to utilize here this second circuit in order to draw the complete equivalent circuit. So this should be known to you, which is discussed here. Now what we will do before combining it, one thing we have seen, when there are two separate circuits, you can refer quantity. We have referred in case of particularly transformer, the secondary circuit parameter were referred to primary side. The same thing we are going to do here, that all the rotor circuit parameter will be referred to the stator side. So when you are going to refer, at that time your transformation ratio, voltage ratio, that is going to play the role. So your referred value of EMF, that will become this one. These are the referred value. Okay, so we have first obtained the referred rotor circuit referred to stator side. Now you can club it. So both the circuit are with you, you can club it. So you are going to get this circuit. So what would happen in this circuit? What you need to basically keep it into mind. This circuit is completely drawn at the supply frequency because all the parameters are referred to stator side. This is an important point. It means whatever voltage you could get here, that will be at a frequency of supply or stator side frequency. Do not confuse. We have already referred all the rotor circuit parameter to stator side. So now the complete circuit, the whole equivalent circuit as at line frequency or stator frequency. See, there is another reason. When you are combining this, rotor is having a different frequency, stator is having a different frequency. So how you can club it? In order to club, it should be at the same frequency. That's why it is referred to the stator side. The rotor parameters are referred to the, we have obtained equivalent circuit on referred to the stator side. This is your general equivalent circuit. In this circuit, what we have done, we have just removed the prime notation. Complex notation is removed, so it seems little easier. You could see in this case. R1 is there, X1 is there. Stator side, RC, IC is there, which is representing your pole loss component. XM, IM, it is representing your magnetizing part. Rotor side, what you could see here, it is your X2, I2, R2 by S. Here, what you need to remember, because notations are removed, it is referred, the rotor parameters are referred to stator side. That you must remember, keep it into your mind, you must remember it. So all the whatever parameters you are here, already we discussed that it should be at, it are at line frequency, supply frequency. Now we are going to obtain, we are having this circuit. For better understanding, we are going to modify this circuit. So in modification, what we will do, we are going to write this R2 by S into two parts. We are going to split this resistance into two parts. Let me show you. Here you can see that R2 by S is splitted into two parts. R2 is there, and R2, when you are going to add these two, you are going to get that value only, R2 by S. So resistance R2 by S is splitted into this one. So this is particularly called as your modified form of induction motor equivalent circuit. Only R2 by S is shown in a splitted form. Here one thing you can observe. When slippage 1 means your induction motor is at standstill condition, rotor is not revolving, rotor is stationary. So when you are going to compare this with transformer, so you will find out this circuit is equivalent when the slip is 1, this is equivalent to a circuit of transformer when it was short circuited. And when your slip is 0, means at synchronous speed, which is not possible basically, which is not possible in the case of induction motor. So when the slip is 0, this circuit will become, when we are comparing with transformer, it will be treated as open circuited equivalent circuit of transformer. So when S is equal to 0, open circuit of transformer. When S is equal to 1, it is equivalent to the short circuit of transformer. Hope the things you are getting. We have seen the power flow diagram where we have shown the power, various power are shown, the losses were shown. If the same thing has to be shown in the equivalent circuit, so here is a thing. Initial part, there will be stator input, R1 is there, so the losses which are going to occur, that is going to give you stator I square R loss. So the copper losses in stator, that will be here. After that, this X1 and RC, this is going to give you the stator core loss. And after that, there will be the air gap power or the power input to the rotor. Then there will be R2, that is going to give you basically rotor I square R loss. After that, this will be here, you are going to get the mechanical power developed in the rotor. Shaft power that can be determined, already we have seen. So what you need to do, you need to just minus it, this value. Shaft power, that will be equal to the mechanical power developed in this value, R2 into 1 minus S into S. Now you could understand why we have split it into 2. R2 by S is split into 2 resistance. So this is going to give you the mechanical power. Just what you need to do, you need to subtract the mechanical losses. So you are going to get the shaft power. Here the quantities which we have considered here, that is per phase quantities. So here we are going to stop.